Universitas Jember is a center for higher education founded in 1964. The motto, Karya Rinaras Ambuka Budi, Gapuro Mangisti Aruming Bawono, is a commitment of the university's founding fathers to produce creative and innovative generation in developing knowledge and to serve the society based on the faith and religion. The university's motto becomes the academic base for the leaders of the university from time to time to adapt and draw near the development of science and technology to reach the position as the center of academic in Indonesia, Asia, and the world. Universitas Jember is located in East Java Province, Indonesia. Sectors such as plantation, agriculture, maritime, health, tourism, industry, arts, and culture. The agriculture and plantation sectors have made Jember famous for its coffee, sugarcane, tea, tobacco, cocoa, and edamame soybean. Jember is also culturally unique with diverse mix of Javanese, Madurese, Osing, Chinese, and Arab culture. For nature laboratories to develop science. Rich and abundant natural resources provide history and phenomena for potential researchers. The potential research and the development of knowledge generate scientists in their own field. Professor Bambang Sugiarto, expert in biotechnology and genetics engineering. Professor Bambang Kuswandi, expert in analytic chemistry, chemosensor, and biosensor. Professor Ahmad Subagio, expert in biotechnology, food sciences, and nutrition. Professor Rudy Wibowo, expert in agricultural economics. Professor Nawianto, expert in economic and environmental history. Professor Slamin, expert in graph theory. Professor Davik, expert in combinatorics, graph theory, and combinatorial education. Professor M. Arif Amrullah, expert in criminal policy and economic criminal law. Aditya Wardono, PhD, expert in Asian monetary, financial, and development economics. Dr. Kartika Sanjarini, expert in molecular biology. Abu Bakar Ebihara, PhD, expert in international relations. By 2018, the university has vast range of programs to choose from 15 faculties, 27 postgraduate programs, and 73 undergraduate studies. To support the objectives of education, research, and community service, and to optimize the nature laboratory potentials around Jember, the university has developed and established branch campuses in two nearby towns, Bondowoso and Lumajang, which enables a well-built connection for the experts to innovate through their studies and researches, which then provide benefit to the surrounding society. The learning atmosphere is constructed not only to produce mere scientists, but also the ones with social awareness and responses to the problems in both local and global society. Dealing with the challenge, the university educates the students through learning, researches, and community service. To support an easy access to academic atmosphere, The students are provided with Integrated Information System or SISTER and e-learning, making them possible to communicate with the professors and to obtain information in seconds through their smartphones. Universitas Jember also consistently collaborates with international experts to share their reputable knowledge through a general stadium for students to open their insights and enhance their knowledge. Universitas Jember also supports students and teaching staffs to broaden both knowledge and experiences through its mobility and exchange programs. Several world-class and reputable universities in the world have been involved and participated in the program, such as Students' Mobility. Such valuable academic atmosphere has driven international students to study in Universitas Jember, including those from the United States of America, Germany, Iran, South Korea, Laos, Madagascar, Timor Cambodia, outstanding international students by providing scholarships like their surroundings, promote wider knowledge and insight Universitas Jember was awarded MDG's Trophy for its contribution to coffee farmers of Jordania's SDG Center to support Sustainable Development Goals. Universitas Jember does not only house one centralized library, rather, each faculty is facilitated with a library completed with abundant literatures on its respected field. The students are also fast access to digital journals hosted by reputable publishers such as Springer and Nature. Universitas Jember Community Service is a compulsory program for students as a training to respond to community's problem. Students are assigned to work in groups with their multidisciplinary backgrounds to live within the period of 40 days among the society. The community programmed twice a year in January and July. The community service enables students to get involved to find solutions to society's problems. Tridharma has greatly supported the development of knowledge, teaching, and learning process through the formal education. On the other hand, Universitas Jember also greatly concerns on students' talents and interests. Student bodies and clubs are available as the best places for students to learn science, arts, interpersonal skill, organization, and to socialize with other fellow students. An excellent and innovative generation to develop knowledge and science for the society within religious perspectives. This is the vision of Universitas Jember to create a better future for mankind. Tradition of excellence. Universitas Jember is a center for higher education founded in 1964. The motto, Karya Rinaras Ambuka Budi, Gapuro Manyusti Aruming Bawono, is a commitment of the university's founding fathers to produce creative and innovative generation in developing knowledge and to serve the society based on the faith and religion. The university's motto becomes the academic base for the leaders of the university from time to time to adapt and draw near the development of science and technology to reach the position as the center of academic in Indonesia, Asia, and the world. Universitas Jember is located in East Java Province, Indonesia. Universitas Jember plays its central role to develop science and technology in various sectors such as plantation, agriculture, maritime, health, tourism, industry, arts, and culture. The agriculture and plantation sectors have made Jember famous for its coffee, sugarcane, tea, tobacco, cocoa, and edamame soybean. Jember is also culturally unique with diverse mix of Javanese, Madurese, Osing, Chinese, and Arab culture. 4 national parks which become nature laboratories to develop science. Rich and abundant natural resources provide history and phenomena for potential researchers. The potential research and the development of knowledge generate scientists in their own field. Professor Bambang Sugiarto, expert in biotechnology and genetics engineering. Professor Bambang Kuswandi, expert in analytic chemistry, chemosensor, and biosensor. Professor Ahmad Subagio, expert in biotechnology, food sciences, and nutrition. Professor Rudy Wibowo, expert in agricultural economics. Professor Nawianto, expert in economic and environmental history. Professor Slamin, expert. Professor Dafik, expert in combinatorics, graph theory, and expert in criminal policy and economic criminal law. Aditya Wardono, PhD, expert in Asian monetary, financial, and development economics. Dr. Kartika Sanjarini, expert in molecular biology. Abu Bakar Ebihara, PhD, expert in international relations. By 2018, the university has vast range of programs to choose from 15 faculties, 27 postgraduate programs, and 73 undergraduate studies. To support the objectives of education, research, and community service, and to optimize the nature laboratory potentials around Jember, the university has developed and established branch campuses in two nearby towns, Bondowoso and Lumajang, which enables a well-built connection for the experts to innovate through their studies and researches, which then provide benefit to the surrounding society. The learning atmosphere is constructed not only to produce mere scientists, but also the ones with social awareness and responses to the problems in both local and global society. Dealing with the challenge, the university educates the students through learning, researches, and community service. To start an academic atmosphere, the students are provided with integrated innovation system or SISTER and e-learning, making them possible to communicate with the professors and through their smartphones. Universitas Jember also consistently collaborates with international experts to share their reputable knowledge through a general stadium for students to open their insights and enhance their knowledge. Universitas Jember also supports students and teaching staffs to broaden both knowledge and experiences through its mobility and exchange programs. Several world-class and reputable universities in the world have been involved and participated in the program, such as Students' Mobility. Such valuable academic atmosphere has driven international students to study in Universitas Jember, including those from the United States of America, Germany, Iran, South Korea, Laos, Madagascar, Timor-Leste, Cambodia, and Thailand. The university is committed to provide fundings for talented and outstanding international students by providing scholarships and support them with extensive Indonesian language training, assisting them to adapt and engage actively to their surroundings. The recruitment of international scientists, experts, and students has been arranged selectively to promote wider knowledge and insights for the surrounding community to make greater future possible. To foster the students' competence to enhance their knowledge, our highly competent professors and lecturers are committed to the development of teaching and learning process. The professors and experts in Universitas Jember have been supporting students to achieve their competence. They are committed to dedicate their time to guide and supervise students' work and to develop students' knowledge. Research groups and Center of Excellence are available to create research atmosphere in each faculty and across multidisciplines. Amongst many are CURIS, CDUST, CHRM2, SIGANT, CIRISH, SDG Center, and Tropical NRC. Our research centers has remarkably increased their productivity since the last 5 years. Our creative and innovative researches contribute greatly to the development of science and society. In 2013, Universitas Jember was awarded MDG's trophy for its contribution to coffee farmers in Sidomulyo village, Jember, Indonesia. The university also established the SDG Center to support Sustainable Development Goals. Universitas Jember does not only house one centralized library, rather, each faculty is facilitated with a library completed with abundant literatures on its respected field. The students are also facilitated with free access to digital journals hosted by reputable publishers such as Springer and Nature. Universitas Jember Community Service is a compulsory program for students as a training to respond to community's problem. Students are assigned to work in groups with their multidisciplinary backgrounds to live within the period of 40 days among the society. Community service is regularly programmed to lie. The community service enables students to get involved to find solutions to society's problems. Tridharma has greatly supported the development of knowledge, teaching, and learning process through the formal education. On the other hand, Universitas Jember also greatly concerns on students' talents and interests. Student bodies and clubs are available as the best places for students to learn science, arts, interpersonal skill, organization, and to socialize with other fellow students. An excellent and innovative generation to develop knowledge and science for the society within religious perspectives and beliefs. This is the vision of Universitas Jember to create a better future for mankind. Tradition of excellence. Universitas Jember is a center for higher education founded in 1964. The motto, Karya Rinaras Ambuka Budi, Gapuro Mangisti Aruming Bawono, is a commitment of the university's founding fathers to produce creative and innovative generation in developing knowledge and to serve the society based on the faith and religion. The university's motto becomes the academic base for the leaders of the university from time to time to adapt and draw near the development of science and technology to reach the position as the center of academic in Indonesia, Asia, and the world. Universitas Jember is located in East Java Province, Indonesia. Universitas Jember plays its central role to develop science and technology in various sectors such as plantation, agriculture, maritime, health, tourism, industry, arts, and culture. The agriculture and plantation sectors have made Jember famous for its coffee, sugarcane, tea, tobacco, cocoa, and edamame soybean. Jember is also culturally unique, with diverse mix of Javanese, Madurese, Osing, Chinese, and Arab culture. 4 national parks which become nature laboratories to develop science. Rich and abundant natural resources provide history and phenomena for potential
Assalamualaikum warahmatullahi wabarakatuh. In the name of God, the most gracious, the most merciful. Good afternoon, ladies and gentlemen. First of all, let's thank God who has been giving us blessing, happiness, healthy, and mercy so that we could attend the summer school program. The Honorable Dr. Boy Arif Fahri, as the head of the Chemical Engineering Department, the Honorable Professor Hai Kolanga from the University of Milano Bicocca in Italy, the Honorable the lecturers of Chemical Engineering Major, University of Jember, also all of the participants of the fourth series in International Summer School on Bio-based Chemicals. I am Yasmin Anissa as your Mistress of Ceremony for today. Today, we gather in the fourth series of the summer school program with the topic Biorefineries as entry point to a more sustainable chemistry, which will be moderated and generated by Dr. Hanggara Sudrajat. As a mistress of ceremony, let me convey the rundown of today's event. But before that, let's pray and praise to God. May this event be held well from the beginning till the end. For the sequence of events, namely playing the national anthem of Indonesia, which will be continued with the opening speech, then we will get into the main session, which is the workshop that will be given by Professor Heiko Lange. Then will be continued with the discussion or the question and answer session, and lastly closing. Without any further, let's start this event by playing the national anthem of Indonesia, Indonesia Raya, where all of the participants are asked to listen quietly. Thank you so much. Let's move on to the next session. This opening speech will be delivered by Dr. Boy Arif Fahri as the head of the Chemical Engineering Department. For Dr. Boy Arif Fahri, time is yours.
Uh, distinguished guests, ladies and gentlemen, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon in Indonesia and good morning perhaps in Italy. First, I would like to welcome you all to our agenda today. We are pleased to host the lecture entitled uh, Biorefineries as Entry Point to a More Sustainable Chemistry in the framework of our UNEJ Summer School on Bio-based Chemical. Now, I would also like to thank to the committee for coordinating this lecture from the beginning. Thank you very much. And I would also like to convey my heartfelt welcome to Professor Heiko Lange from Universitas Degree Studi di Milano, Italy, for your participating and for your uh, support in this lecture. My heartfelt welcome to you, Professor Heiko. And yeah, hopefully in the near future, we can perform some collaboration in the area of research and lecture. Yeah, because the topic is very attractive and sophisticated. And yeah, and the topic also in line with our vision mission in our research, which is focused on the bio-based chemical product. So I think it's a very good initial step to perform further collaboration in the near future.
I would be very happy. Thank you very much for the welcome. Thank you very much.
Thank you. And I would like also to thank to the all participants who already joined for the very first time for this summer school, because today is the I think it's the fourth series from our summer school. So again, thank you for all the participants who joined this program from the very beginning. I really appreciate it. And hopefully in the end of the program, you can gain more insight from our summer school. And again, for my student or for all the participants, if you have any question, anything to ask related to the topic today, please wait for our Q&A session, and don't hesitate to raise your hand and or write your question, and then the committee will deliver and display your question. Because don't lose the chance to explore the topic related to biorefinery concept. And the last but not least, I would say to all of you, enjoy the lecture and good luck for the lecture. Thank you very much. Time and display, I give it back to the Yasmin. Thank you very much.
Thank you so much for the speech. Ladies and gentlemen, now we are coming to the main point of this event, the fourth series of University of Jember International Summer School on Bio-based Chemical, Biorefineries as entry point to a more sustainable chemistry, which will be guided by Dr. Hanggara Sudrajat. To Dr. Hanggara Sudrajat, time is yours.
Okay, okay. Thank you, Yasmin. Good afternoon, everyone, and good morning to Professor Heiko Lange in the University of Milano Bicocca in Italy. I'm Hanggara Sudrajat, Professor. I'm Hanggara Sudrajat from the Chemical Engineering Department, and also the chair of the 2021 Summer School on Bio-based Chemicals. So today we come to the fourth lecture series in our summer schools, even though it's no longer summer actually. Anyway, so far we have discussed a range of topics from biorefinery to bioenergy. So today we will be also talking about biorefineries. We have here Professor Heiko Lange with us. Professor Heiko is an associate professor for general and organic chemistry from University of Milano Bicocca. He got his PhD in organic chemistry from the University of Münster in Germany, followed by postdoctoral research in the University of Cambridge in UK and in Harvard University in the US. His research area is primarily on designing flow chemistry approach. He also develops strategies for characterization and valorization of polyphenols. So today he will deliver a very important topic for us, which is biorefineries as an entry point to a more sustainable chemistry. So if you have any comments and questions, you can use the Google form that we will provide here in the comment section, or you also can ask him directly. Okay, so Professor Heiko, time is yours.
Okay. Thank you very much, Professor Sudrajat. I'm very pleased for the invitation. I'm very thankful, honestly, that you give me the opportunity to present my research here, which I'm working in that field since nearly 10 years now. So what I will give you now in this lecture, let me share my screen, is an overview basically on the research that we did over the past years. So I hope you can see my slides. Can you see my slides?
Yes, perfect.
Okay, perfect. So let's go to the beginning then. So move slightly to the side. Okay, so I'm as you just kindly introduced me, I recently joined the University of Milano Bicocca. I was working actually before in Rome, in Italy, working on the same topic. And so I'm still in the transfer of my laboratory, to be honest. So it's you might know that's always difficult. So, but anyway, let's start. So as the title of the talk says, I'm going to talk about biorefineries very, very briefly, because I just would like to mention a very major point when it comes to the research, and especially to the work with polyphenols in the context of generation of maybe platform chemicals, in doing material science based on these polymers. So from my background, obviously the chemistry plays the crucial role, and I'm very convinced that without understanding the structural features, for example, of a biopolymer, there's no way that you do anything useful out of it, because at the end of the day, we're manipulating on a chemical or physical-chemical base. So the chemistry plays always a key role, and that is basically my group is based on this chart practically. So the chemistry is at the center, and from the chemistry starting from the chemistry, we develop novel smart molecules, biomacromolecules. We try to understand interaction, modification, and recognition in order to get the best out of the polymer that is provided by nature. Doing this, we can foster generally sustainability by working on synthetic methods, working on downstream biorefineries. So we're not necessarily doing the biorefinery on the big scale, but we're trying to develop technologies that are compatible with the current production, with the current biorefineries, in order to then downstream do the first valorization practically. We can produce functional polymers, smart materials, or just materials, and we even endeavor now some projects in the range of drug design and diagnostics. So let's first go to the downstream biorefinery. I mean, if it comes to I will basically talk about lignins and tannins, but obviously, other people working more in the field of cellulose can do the same discussion on the field of celluloses. So if it comes to the biorefinery processes, obviously we have the various feedstocks. You see typical feedstocks here, and these feedstocks do provide, at the end of the biorefinery process, the lignins. However, the question is, or obviously, as you might already know, one lignin is not like the other lignin. That is a function of the feedstock itself, and that is a function of the biorefineries, and that is where the problem starts, basically. So the biorefinery basics are always the same, right? The idea is the same. So we take the feedstock, we do some maybe some pre-treatments, we remove residues that we do not like to have in there. For example, if it comes to wood that has been already used, we have to get rid of the metal of the nails inside. For example, if we want to recycle wood, we can always do then the fractionation of the biopolymers, of the major biopolymers, and then come to products which are derived on the basis of the chemical characteristics of the biopolymers isolated. However, whatever looks nice in a principle chart like this then becomes a problem if we go to reality, because obviously, as I said, the feedstocks vary, and then the philosophies vary. And the methods vary that are more or less used in different settings and according to the feedstocks, etc. So we have pre-treatment methods like this one, for example, which would be a general chart for a steam explosion pre-treatment, where we try to more physically than chemically or physico-chemically, depending on how you run it, disrupt the biomass in order to facilitate eventually later fractionation of the of the principal polymers of the biomass. Then we have the classical, for example, craft processes in the pulp and paper industries. This is a flowchart that describes the latest or the LignoBoost craft process, which is, especially here in Europe, one of the major processes, obviously in Scandinavia, where they have all these forests. The paper industry is relying on this process. And what we get in terms of polyphenols are obviously then the lignins out of the black liquor. But as you can see, the LignoBoost process is made for getting the highest quality papers, right? Or paper, cellulose. The lignin is just a side product. So we have to deal with it. Whatever happens to the natural polymer in this process, in the first part of the process, is what we get out of it, right? And that has nothing to do, this lignin, which is in here, has nothing to do with the lignin that we find in the trees, for example. So that is one of the major problems. It's a problem in the craft process, but it's a general problem in all the biorefinery processes. If you go, for example, to the more modern CIMB organosolv process, it's organosolv, so it's a very different type of chemistry, the idea of getting the lignin separated from the cellulose and the hemicellulose. But at the end of the day, it's a chemical process. So again, a chemical structure provided by nature is reacting to the conditions that I'm using in order to get my different biopolymers separated. And also this process, although being, let's say, from a chemical point of view, much less severe than the craft process, is still chemically altering my is still altering my my chemistries of the biopolymers, for example, right? Same is then true for the production of lignosulfonates, and lignosulfonate is one of the rare cases where actually the name already indicates a structural change of the biopolymer, right? It's not called a lignosulfonate. It's normally not part of the lignins. It's, as I said, the name with the sulfonate attached to the lignin is already indicating that also in this process we have severe chemical alterations of the natural lignin structure. And obviously, I have to account in my research to these or for these differences in chemical structures that originate not only from the biomass that I might choose, right? Whether I use wood or whether I use annual plants, etc. But I do have to be concerned about the chemicals, the changes in chemical structure of the lignin that is caused by these processes. The cellulose, due to its nature, it's much less altered in its structure, obviously, right? So the problem originates when you come especially originates when you come to the lignin. So, despite all these problems, the question is, why are these lignins or also tannins, so generally natural polyphenols, interesting for material science? And you might already, you for sure all know that that lignin is the only biopolymer that contains actually aromatic units in abundance, right? So it's a very interesting starting point for the generation of aromatic platform chemicals, for example. But it is due to its aromatic nature, obviously also very, very interesting from a materials point of view. The fact that these aromatic moieties are present in the form of phenols gives us lots of other biologically interesting properties. So we have to add to the interesting physical properties, to the interesting chemical properties, also the interesting biological properties, which are, for example, the UV absorbance, the antioxidant activity, and then obviously when it comes to tannin, also eventually bacteriostatic activities, bactericidal activities, depending on how you tune it. So altogether, it's a very promising, let's say, group of compounds, these polyphenols, but as indicated, you cannot do much with them if you do not understand the structure. So a lot of work in our research is actually targeting a structural understanding, because this is a typical structure you see very, very often in presentations. It's a generic lignin structure. It's not all wrong, obviously, right? But the question is whether this structure is really a generic structure, and whether using this structure for getting an idea of the biopolymer lignin is actually a good idea. Because the question is, now you see the structure, it's obviously polymeric, right? It's indicated that it might be even bigger than this. It has already something around 20 units. That would be really a polymer if every monomer unit as a C9 unit in lignin weighs around 280 grams per mole. So that would be a real polymer, quite heavy, huge molecular weights. So the question is that really a representative structure of the lignin of these powders that I showed you before, right? So is this chemical structure really reflecting the chemical nature of these powders? Now, different colors, because they might stem from different feedstocks, but above all, the colors are originated as chemical degradation during these processes. I don't know if you know that lignin, if you do a very, very careful isolation in the laboratory, lignin would be off-white. It wouldn't be brown or nearly black, as you often see it when you go for commercial sources, but it would be actually a rather white substance, because technically in a lignin structure, if you think of it, there are no chromophores, right? You have the aromatic units, but those aromatic units are not chromophoric. So there's no way that this structure, which would look like this, would give us a brown color. So even from this simple consideration, you can already see that such a structural representation as you see here has nothing to do with the brown powder you actually have, right? So there must be structural changes to this during the different processes. This might be a natural structure of the lignin in a tree, for example, but it's not the brown powder that we actually get out of a biorefinery process to do our work with, right? And that is the basic point. So we spent, as I said, a lot of time on structural characterization. We do this structural characterization normally in form of NMR. So we do a lot of 2D NMRs, HSQCs. We have developed in the past a method to do quantitative HSQCs for lignin. We didn't develop the method, but we managed to adopt the method that was developed for pharmaceutical biomedical studies on proteins to the polymer, or to the oligomeric or polymeric lignins. If you do that, you get quantitative HSQC data, and the problem is that it requires a cryoprobe and at least a 600 megahertz NMR. So it's not, for example, now I have a 600 megahertz, but I don't have a cryoprobe in it. So this method cannot be done everywhere. So we did that at the European NMR Center, normally these measurements. And there is another method which is much more feasible, which is doing a quantitative carbon NMR and then quantifying in the second stage a very high quality HSQC that has not been run in a quantitative sense. So that works equally well. We did some comparative studies and the results are absolutely, now within the error, the results are the same. So we use now by default the other method because it's just quicker to get. We run a lot of phosphorus NMRs. The phosphorus NMRs are run, obviously the lignin doesn't contain any phosphorus, right? I mean, the structure that I showed you before is correct in the sense that apart from carbons, oxygens, and hydrogens, there's nothing in the lignin, okay? Natural lignin doesn't contain, for example, neither sulfur. Sulfur that you might sometimes see in elemental analysis, or that you might correctly or incorrectly see in chemical structures, are obviously these atoms, these sulfur elements are brought in during the biorefinery processes. So technically you wouldn't expect any sulfur, neither nitrogen, obviously, in a lignin structure. So we do a lot of phosphorus NMRs in order to get on a phosphorylated sample. So we have to modify our structure, our lignin structure, in the sense that we phosphorylate the hydroxyl groups, and we do then phosphorus NMR on the phosphorylated lignins. And the method has been, also this has not been invented by us, but we adopted again an existing analytical method to the analysis of lignin. The method has been developed in the 70s in the 70s to analyze actually impurities in oil. So someone took oil and phosphorylated oil samples and saw that different alcohols, thiols, amines, etc., that you might have as impurities there. In wild mixtures, they give you different shifts once you phosphorylate. And if you obviously, if it works for that, it works for lignin, right? So what you see in the NMR is you get that the signal shift according to different surroundings of the phosphorylation of the phosphorylated hydroxyl groups. So a primary hydroxyl group has a different surrounding than a secondary and then a phenolic. And you actually see that in the shifts. So this allows us to actually, you can do that in a quantitative way. So this allows us actually to get information on the OH, on the hydroxyl end groups in a lignin. So how many phenols do we actually have? How many free phenols do we actually have? How many free primary and secondary aliphatic hydroxyl groups do we actually have? And we even see acids. How many carboxylic acids do we actually have? That is obviously, apart from the, now let's say the more detailed structural features, one very important information, because the hydroxyl groups are obviously the first points to target in any chemical functionalization, for example, right? And if it comes to UV protection or to biological activities, it's especially the phenolic OH groups that are interesting. So these two NMR techniques are key in order to get an idea of the structural understanding. Without any, it's not very easy to get out of these NMR studies information of the molecular weight. I mean, you could do some calculations, etc. But for getting ideas on the molecular weight, you know that GPC, so gel permeation chromatography methods, are much better in order to actually get an idea of the molecular size of your lignins. Obviously, GPC is not a very exact method, right? It's you have to do a calibration. The calibration needs standards, and the problem with lignin is that the standards for lignin that you do not find standards that really represent the lignin structure. We said that the lignin structure might be similar to this, but it is not this, right? And how do you want to get a standard with a confirmed molecular weight that has this type of structure? So that is eventually synthetically, chemically, if you really, really want, you can polymerize different now cinnamyl alcohols, etc., in order to get something like this, but it's practically it's not feasible. So the question is, how do we find the right compromise between the lignin structure, so it will always be a polyphenol, and the GPC standard? And the answer is that there is no perfect solution, obviously. So the best thing you can do is to use a general calibration for your GPC method, for your chromatographic method, and then refine it with some isolated small polyphenols, which are structurally much more defined. For example, tannins or synthetically derived dimers and trimers. And that is what we normally do. So we calibrate very carefully our GPC. We try to get a calibration as good as possible, and then we run our analysis. This gives us then some, let's say, more or less reliable information on molecular weights. Nowadays, obviously, if you have the possibility, there might be some chromatographic methods that use, for example, light scattering detectors, etc. They a little bit improve on still the situation. So you can get very good molecular weight data for lignins, and those are obviously key, because also those help you to decide whether such a structure would be actually a structure to trust. Then, when it comes to material applications, we obviously are also interested in thermal data, right? So we need to know what is the glass transition temperature, and for example, what is the decomposition temperature. So we run also DLC TGA to have an idea. Nowadays, since a couple of years now, I work together with a university in Scandinavia and 2 universities in Scandinavia, and we do also pyrolysis on the lignins, just in order to get an idea of the stability. With all this, you then have to create, obviously, based on This is the HSQC as I okay. This is the HSQC as I said. You might know these famous pictures of the HSQCs. You can also color these, right? If you look at standard publications by John Ralph's group. I mean, you know, John Ralph is one of the pioneers in lignin research, right? He introduced this nice coloring. Sorry. Huh? Okay, there you have these nice. You have this coloring of these pictures. And then it becomes a little bit more clear. I have a picture that looks like this, right? This is the same HSQC. So you can color different, if you want to highlight where some groups are, you obviously can color them, and you have these typical patterns for lignins, and in this case for extractives. So this was just the GPC. One last comment to the GPC is obviously that a lot of people report, for example, a functionalization of the lignin before they run the GPC. The reason for this is that often the lignin structures, which might be this or might not be this, are not as soluble as you would expect, also based on this structure. Like if you look at this structure, you see a lot of OH groups, so you expect and the aromatics, so you expect the bipolar character, so technically you expect the solubility. But often the solubility of lignin is very poor, especially of the isolated lignins that you can buy. And so a lot of people do functionalization of the lignins. And one of the current functionalization, or often reported, is an acetobromination. An acetobromination, however, from a chemical point of view, and that brings us once more back to the original problem, is a chemical alteration of the structure. So if you do the acetobromination, what you actually analyze is not the lignin. It's not even not the lignin that is in the tree because it underwent biorefinery. It's not even the lignin that you buy, because you did another secondary chemical functionalization of that lignin. So at the end of the day, what you are analyzing is a polyphenol that contains acetate groups and that has been brominated on the secondary OH groups. So this is very different. And what we could see in our laboratory is that such a functionalization, such an acetobromination, actually causes shifts in the peaks. So even on the same calibration, depending on which functional group you have, and you acetobrominate or you just acetylate, you shift. So the molecular weights that you might get out of this analysis contains an additional error just because you had to functionalize it. So the better way to do GPCs is to find a system that works using the lignin without further and it's still another type of chemical derivatization. Doing all this, then you come to some structural findings. And the structural findings can be further, can be further quantified or validated using fractionation methods. So fractionation methods are actually, as you might know, are used in order to solve the problem that the biopolymer lignin, generally the polymeric polyphenols, display a huge polydispersity. So normally, if you go for materials applications involving polymers, you would like to work with polymers that have a rather confined polydispersity. In terms of lignins, isolated lignins, the polydispersity is comparably huge and not suitable for high quality applications if you go to material science and you want to use the polymeric character. So it was, let's say 5, maximum 10 years ago, it became an idea again, because it was already an idea in the 50s, 60s, to fractionate lignin. So I take lignin as it comes, as I get it as an isolated form in the brown powder, and I treat it with various solvents in order to wash out practically various fractions that are soluble in one solvent rather than in another solvent. So you can do that in order to tune molecular weight properties, especially polydispersities, and you will see that you get fractions of lower, medium, and higher polymer molecular weight, and that's it, right? That is the easy way to fractionate. From a chemical point of view, again, no, I'm sorry, I'm chemist, so I look at the things from a chemical point of view. So from a chemical point of view, the different solvents clearly interact differently with the different structural features of the lignin. So what do we have as structural features of the lignin? We have the polymeric character. That's okay, fine. But we have OH groups that are aliphatic or aromatic. We have acids, we have various linkages, we have tetrahydrofurans, etc., as structural motifs that form during the polymerization naturally, etc. So we have a certain, let's say, eventually a polymeric form, in a certain spatial form in which the polymer actually exists in our solution, right? Because we have all these functional groups in one polymeric molecule. So it would be actually wrong to think that the polymeric molecule exists as a linear chain in our solutions. If you provide a solvent that is not able to interact with the polar groups, probably these polar groups will interact themselves among themselves in intermolecular fashion. So you will actually have eventually spheric particles, right, which display towards the outside the type of polarity that goes together with the solvent you're providing. So the question is, how do you actually fractionate the lignin? Because if you think of that, you have to think of concentration issues, of polarity issues, obviously, in your solvents, etc., etc. So it is not so clear on what chemical or physical basis you actually do the fractionation. So it works with the molecular weight. So if you're aiming for molecular weight, then let's say it also works for molecular weights, and you get your limited fractions with the narrower polydispersities, and that's what you wanted, and you move on. But from a chemical point of view, as I said, the thing is much more interesting. So we started to do refinements not looking at molecular weights. So we were not really interested in molecular weights, but we were much more interested in seeing whether a polar protic solvent is fractionating differently than an aprotic unpolar solvent, for example. So we will play with H donor and H bonding donor and H bonding acceptor, for example, characteristics. And we use two solvents, in this case, acetone and methanol, and we tried first to fractionate with acetone, and then the fractions that we got out, that would be a standard fraction, right? If you do the SKL is for softwood kraft lignin, so if you do a fractionation of softwood kraft lignin, with acetone, you get the classical, or by now classical fractions of kraft lignin. If you do the fractionation then later of these acetone fractions, later another fractionation with methanol, for example, you get novel fractions, right? And they have actually, they show you that in these standard acetone fractions, there are still hidden fractions in there that technically you wouldn't expect to be in there, right? So it becomes a little bit more complicated, obviously, because you do a lot of secondary fractionations of fractions, but it's getting interesting because you get fractions where you have a clearly donating H bonding character, and where we can say that we have intermolecular H bonding that dominates. And we have, for example, fractions where we have a mixed donating and accepting H bonding character. Or again, a mixed character, but we have intramolecular H bonding that dominates. So based on these fractions, you could choose one of these, or based on these, and let's say conclusions that you have to draw out of the results. If you also look at structural features of these fractions, you might actually choose these fractions much more targetly for any type of application that you're looking for, right? So if you want to have, for example, a polymer that has a donating H bonding character, and you base your research on such a characteristic, then no way that you work with a fraction that comes from a methanol fractionation, right? So that is obviously something from a chemical point of view that has to be considered. And it was actually very interesting to see these results. We got these results playing also with combinations of extraction or fractionation methods. So, I mean, the normal thing would be, for example, to do a membrane filtration. That is a standard fractionation technique using different cutoffs of membranes. Those go strictly for molecular weight, right? They normally do not care much about functional groups. But in case of lignin, as I said, if you consider intramolecular interactions, then also these cutoffs of the membranes might be less or more efficient. So playing also with a combination of membrane filtering and traditional SOx-led extractions, because also a SOx-led thimble made of cellulose is a type of filter, same effect as a membrane practically. So playing with combinations was actually very interesting to delineate these characteristics. Then if you go for more simple protocols, you can always try to adopt an existing protocol to another type of lignin, which obviously from a chemical point of view, given all the implications of the isolation methods, etc., might not work as well as it worked for one lignin, might not work as well for another lignin. So we actually did a very, let's say, very straightforward adoption of a Kraft lignin fractionation method already years ago on a wheat straw lignin. And what you actually see is that we get, if you would directly compare it with percentages, for example, of the various fractions for a Kraft lignin, you see that in the wheat straw case, in the wheat straw organosulf case, we get very different percentages. So we have a huge amount of insoluble lignin in acetone. So that means also, again, this is another indication that obviously chemically there is no way to compare a Kraft lignin to, for example, a wheat straw organosulf lignin. Wheat straw is wheat straw, so an annual plant. So we have a completely different type of lignin with all three monomeric units present, whereas, for example, in a standard softwood Kraft lignin, we have only G-type lignins, so only guaiacil type monomers. That plays a crucial role in the processing also of the different feedstocks and leads to the fact that in a fractionation, I get very different characteristics. I can then analyze structurally with NMR, GPC, etc., as I said before, all these fractions to get an additional idea of the structural features of your lignins. If you do the isolation right, before you analyze actually, or during the analysis and fractionated analysis also of your lignins, you might find a way to wash out some impurities that are a little bit annoying during the lignin analysis. One of these impurities, for example, are the famous or ill-famous LCCs. LCCs are lignin carbohydrate complexes. So in the, if we go back to the idea of how the lignin is in the wood, actually, I mean, you know this, I mean, this is one of the thousands of pictures you get in this type of way. So obviously we have the together of the three biopolymers, and we have the lignin, which is eventually linked chemically to the hemicellulose. This is still a little bit an issue, or it's still debated how that is linked, because the problem is that from an analytical point of view, it is actually very difficult to prove this linkage, that this linkage exists. Even if you can prove it analytically, you would still have to prove that the linkage exists in the tree, right? And that has not been created during the biorefinery. So that is part of the discussion. Probably they exist. So we have LCCs, we have these chemical interactions between sugars and lignin. We definitely have them in the isolated lignins, more definitely have them in the isolated lignins, and we can actually filter them out. In a fractionation process, this worked very, very nicely. The benefit is, as I said, once you got rid of your LCC fraction, so you isolate the fraction which contains the LCCs, you have all the rest is lignin without sugars in it. So you can actually do the analysis of the lignin free of these type of impurities, let's say, right? Because the LCC is not, lignin is not a cellulose, but it's probably a thing on its own right. So it has its own properties. There are now emerging more and more biological studies that actually show that there's a benefit having the sugar and the lignin obviously in the same, still more manageable little molecule or oligomeric part. Anyway, so this brings us to a purified lignin practically that we can then structurally analyze. If you then, this I skip for the second because I would like to show you first now the structures. So if you do the analysis then, and you spend enough time to do it, this is not done in 5 minutes, obviously, unfortunately, you come up with much more reasonable structures for the different isolated lignins that are normally subject to studies, to material science, etc., and that are At the moment, and probably for the next couple of years, those lignins that are technically available in quantities that would justify their use as a starting point for large-scale material or chemical production. So these technical lignins are obviously kraft lignin, which comes from the pulp and paper processes, and then modern organosolv lignins that are produced alongside the production of cellulose for fuel production, right? So there are nowadays also emerging some biorefineries which are called the lignin first biorefineries, but those are not yet producing lignins on a large scale. So what we have to deal with for the moment are lignins that are technically available, eventually on scale. So that would be kraft lignin, eventually some organosolv lignins and lignosulfonides, right? So it would be very important from that perspective to at least know the structure of these lignins. And there are lots of groups working on this. No, we're obviously not the only ones, and obviously interpreting analytical data leads to common findings, but then some data can be interpreted also in more than one way. So what I will show you on the next slides are the structures that we think represent, from a chemical point of view, actually the isolated lignins. So this is, for example, what you see here is the structure of softwood kraft lignin. So this is actually the lignin that comes out from the pulp and paper processes. And the most important aspect in this is, which you can confirm by various fractionations, that you have that you have parts of this lignin being really polymers, okay? And another part of the lignin is everything else but polymers, but it's rather oligomers. And these oligomers are, in addition, not displaying anymore the typical structural units that you would expect for a lignin. Right? The typical structural units that you expect for a lignin are shown much better in a steam explosion organosolv mixture, for example, or just in an organosolv lignin. Here you see structural features which are typical for lignin. You have these annihilated furane rings. You have these classical beta or 4 groups here. We have some double bond moieties. We have some linkages between aromatic units. So this is more or less a lignin that contains the typical structural features of lignins, and structural features especially of lignins that are also those that you would find in the lignin that is still contained in the plants before isolation, because an organosolv process changing the chemical structure, clearly changing the chemical structure, is however not changing the chemical structure to an extent as it happens in the kraft process, right? You see here, there's nothing left of these typical features. Maybe eventually, if these structures represent the abundances of the groups according to NMR, to quantitative NMR studies. And as you can see here, we have mainly condensation, right? These are all products of various condensation and oxidative coupling reactions that are clearly signs of a severe chemical degradation during the kraft process. And only the larger fraction that is left over contains still some typical original lignin units. So chemically, this kraft lignin is very different from an organosolv lignin, right? And an organosolv lignin is probably much closer to the lignin in the tree. So that is very important to actually understand, because kraft lignin is the major source of lignin at the moment, of technical lignin, right? It is available without any problem. It doesn't cost a lot. So this is a very attractive lignin, for example, for all the industries that would like to substitute petroleum-based chemicals, polymers with some natural polymers, right? For example, if you think of tire manufacturers, etc., they like to work with kraft lignin. Organosolv lignin, chemically very, very different, is maybe the better lignin if you want some characteristics that are more typical that you would expect on the basis of a theoretical lignin structure, right? Because as I said, this is less severely degraded during the processes. This is also important if you do some studies, if you would like to work in a field like the production of platform chemicals on the basis of lignins, because obviously here an enzymatic or biotechnological approach, enzymatic degradation, etc., is very different than on this structure, right? If you go for a natural enzyme, if you, for example, if you want to do a lactase-mediated degradation of lignin in order to arrive at monomeric or dimeric species that have the potential to become the starting point for the generation of platform chemicals, you might want to go for this rather than for Kraft lignin, because obviously the natural enzyme can deal with the natural linkages in lignin, right? If you go for an enzyme isolated from a white rot fungus, for example, that lives on trees, right? That grows on trees. The trees have the natural structure of lignin, so those enzymes in that fungus can deal with beta-4s, for example. They do not know what to do with these structures. It's just not chemically just not fitting, right? So understanding the chemical structure also gives you an idea what lignin to use for tests, for testing biotechnological approaches for lignin valorization, etc. So it's really key to have a technical and a chemical understanding of the structures. Once you have that, you can start playing, right? And in the second part of the talk, I would like to show you what you can actually then do, delineate, starting from the structural, let's say, insights that you got. So one of the things I like to do, as was mentioned, I grew up as an organic chemist. By training, I'm an organic chemist, and I like machine-assisted chemistry. So I like doing chemistry in flow and using flow technologies, and I'm still doing that. I'm not only working with lignin. I'm still continuing the work on RPs, for example. I was together with the University of Naples, where I worked. We developed flow chemical routes to RPs, etc. So I'm still doing that, and I try to use flow chemistry to do lignin modifications. So flow chemistry, I don't know whether you know that. Flow chemistry is basically nowadays, let's say 20 years old as a concept. So you use polymer-supported reagents, you use little tube, you use meso microscale tubing. Basically, you use equipment that is very similar to HPLC equipment, right? And you can do chemistry with these equipments. Nowadays, there are companies that then put everything together. It looks nicer, right? But at the end of the day, you have two pumps, you have injectors, you have sample loops, and you have, where you can see it eventually here, you have reagent loops, right? So this looks nice, fancy, etc., but at the end of the day, it's an HPLC setup. So you can do lignin chemistry or just chemistry with these setups, and you can do it in the field of lignin research, and it looks much less fancy in this case, right? This is our HPLC. I just that we had in Rome. So I took it, I modified it according to my needs, and we did lignin chemistry on that. So for example, we could do lignin fractionation. So we don't do continuous fractionation of lignins in flow. If you do a normal fractionation, now you take a kilo of lignin, you dissolve a part of it, you filter, you dissolve, you precipitate something else out of the filtrate, you filter, etc. So it's not a continuous process. It takes a lot of time and it takes a lot of solvent. So industrially, not very interesting. So we did that therefore in flow. And it is quite easy. You put the lignin in a column, for example, which can be one of these HPLC columns, which you can fill yourself, or a glass column, etc. And we use a pump that is able to mix solvents. And then we pump different solvent mixers across this column, and we wash out different fractions of the lignin. Knowing the structure, we can obviously play with the solvent mixtures. For example, we could play with mixtures of acetone hexane as of the standard system, or we play with mixtures of water, ethanol, etc., to wash out different fractions, either separated according to functional groups or separated to molecular weight features, depending, using, as I said, chemical insight and findings also obviously by colleagues working in the field. And we do a continuous fractionation of lignins that helps you to actually produce larger amounts of fractions, and this is technically industry compatible because it works continuous. If you use the right technologies, you use here a column switcher, and you switch, one column is loaded while the other, or one column is loaded while the other one is currently being used in the line. So you have a continuous production practically. Then the flow allows you to use for fractionation actually conditions that you couldn't use in a batch process if you do the normal solution filtering stuff, etc. Because in flow, you can place a back pressure regulator in line, and that allows you to work under critical conditions. So I can work with acetone, for example, at 70 degrees, something that is not feasible in Soxhlet setups or in infiltration setups, right? Because otherwise it just evaporates too quickly. So working in flow, we can actually play with temperatures, and here you see the difference that it makes. So it's the same fractionation protocol. We took a standard Kraft lignin, for example, and we used different ratios of acetone hexane. Once we used it at room temperature, so that would mimic, for example, the typical conditions you have in the very classical fractionation settings. And we did it at 70 degrees, putting a back pressure regulator. So, and as you can see, when we use higher temperatures with the same solvents, we can actually get a much better resolution in the fractionation, right, from a molecular weight point of view, because these are obviously also all GPC profiles. So we can get a much better separation, a much higher resolution. So in terms of really fractionating, so producing eventually starting materials of different molecular weight characteristics or functional group characteristics, working in a machine-assisted setup is actually giving you a real benefit, right? And this resolution can be even maintained if we double the flow rate. So here, 1.5 milliliter, we actually, it looks still a small number, but you actually start producing in a reasonable scale, right? So we think it's a very promising technique, and that is definitely something we are developing further now. So let's go to other applications. Other applications might benefit actually from a database, in the sense that not everyone has necessarily the possibility to get the lignins, to analyze the lignins, and has the time to analyze the lignins. But maybe you're more into really materials generation. You have the idea that lignin might be a suitable replacement for another polymer you're actually using, or might be a new polymer for a new type of material that you have in mind. Maybe you're not a lignin expert, which is perfectly fine, right? There's much more other things to do in the world. So our idea is, and that is a long-term goal, to create a functional lignin database. So lots of the research that we do in terms of characterization of lignins, trying combinations of biorefineries, analyzing the products, etc., is actually meant to create us input data to get a lignin database working, right? Because we would like, at the end of the day, present something that allows you to get an idea of the lignin structure based on very few key parameters, or have very few key parameters in hand based on a very basic analysis, for example, and to have an idea what structure would that correspond to. And that's such a functional, that's why I would call it functional database, is something we would like to create. And in this functional database, obviously go in then also not only structural features that give me a picture, like, as I just showed you, but we also would like to add in this database thermal data, very characteristic thermal data. And the reason why we think it works is that we did a comparative study together with Anna Tubetskaya that now works at Aalto University, that different lignins give actually very, very different responses in TGA or DTG, for example, right? So there's a type of fingerprinting. So the chemical structure is actually reflected by the temperature response in these DTG settings. So if that is, and we think, I mean, that is just not a case. That must be something obviously more principled, and we are very interested in that, because it would allow us eventually, or it could be a fingerprinting, right? So it may be one DTG analysis based on a database would allow you to have an idea of the structural features of your lignin. And once you have the structural features of your lignin, you might be able to decide whether fractionation is something to pursue in order to get the polymer you want, right? Or what type of fractionation you then need. So this, the setting up of this database is actually one of my long-term goals, right? And the work that we're doing at the end of the day, hopefully brings us in a position to create that. So this is just a slide to show you the idea of the database, obviously, right? Let's talk briefly about tannins, because obviously everything I just told you in terms of lignins is also true for tannins. Here, the field is, however, a little bit different from in the respect that tannins, from a structural point of view, are much less complex. They are still complex from a chemical point of view. The structures are nicely complex, but there's not this wild structural diversity as you find in lignins, because the tannins are secondary metabolites, have a very specific focus, right, to protect the plants mainly against pathogenic attacks. Then within us, when we eat, in our diets, the tannins that we eat obviously help our organism also in order to fight against radicals, to fight against bacteria, etc. So in terms of tannins, we have two classes, condensed tannins and hydrolyzable tannins. The condensed tannins can be esterified here, so we get a hybrid structure, which is actually called complex tannins, right? These are typical tannins. This is a typical tannic acid. These are flavonoid proanthocyanidin tannins, and they exist as monomers, dimers, and trimers. Higher than that is can also be found, but much less. So then obviously these tannins may just in green tea, for example, right? In coffee, some tannins, in wine and in grapes are tannins, etc. So these tannins have to be structurally understood for doing material science with them or chemical variations, obviously, as much as the lignin structure has to be understood. So I have to know which type of tannin do I actually have, class A, B, or class C, and then how big is my tannin? So do I actually have a monomer, dimer, etc., and eventually, which subtype do I actually have? Do I have 3 OH groups here? Do I have only 2 OH groups, etc.? So what we can do is we use basically the same machinery, the same toolbox as we had for the lignin. So we run NMRs, 2D NMRs, phosphorus NMRs. We run GPC. In case of tannins, we can also do MALDI analysis. MALDI-TOF analysis on tannins is possible, and it gives, because the structural features, it's oligomers, not polymers, so we actually have a chance to see something in a MALDI. Whereas the lignin is very difficult to analyze in a MALDI. You would only see the low molecular weight fractions, right? The high molecular weight fractions do not fly. Even, I mean, you can try, but it's really tricky. So MALDI-TOF analysis works much better for tannins, and we actually can then get really detailed structural analysis of tannins that allows us, for example, to take a commercial tannin and to verify or falsify the structure of this commercial tannin before we actually going to use it for anti-biofilm production or production of surface active materials. And this is very important, right? Because obviously it makes a difference whether you have a classical tannic acid like this or whether you have a quinic acid, right? It's both a hydrolyzable tannin, but in terms of molecular size and in terms of structural characteristics as a polymer or oligomer, it makes a difference, right? So this is basically the same idea as with the lignins. First, you have to know the structure, then you go for applications. So once you know all this, we can think of synthetic methods. So how can you actually manipulate the structures? And we can use that in order to make platform chemicals from lignins and tannins, for example, by biotechnological or classical inorganic catalysis. This is the work we recently did together with a Spanish group. So we take molybdenum or vanadate complexes. We take, in this case, it was a ionosulf lignin. So ionosulf lignins are not identical, but similar to organosolv lignins in the sense that they display the typical lignin groups, functional groups, and functional structural motifs, not so heavily degraded. The problem is with ionosolv lignins that you often have the residues of ionic liquids in them, because as you know, ionic liquids are nice from a certain point of view, but are very, very difficult eventually to remove, right? And the sustainability aspect that they might bring with them, or the green chemistry aspect from one point of view, might actually be completely destroyed by the need of excessive washing at the end in order to remove them. So ionic liquids are might be helpful, but not always. In this case, the Spanish group isolated some lignins using a ionosolv process that they developed, and we tried their ionosolv in catalytic degradation. And we actually found interesting results, because this ionosolv gave us not a very wide series of products, but was actually very, very nicely degraded in the sense that we got a few products which were actually technically useful as platform chemicals. So this is a very interesting step, and we are that was a very interesting finding, and we are now trying to make more out of that using other catalyst systems, and eventually trying to use this system together with machine-assisted setups. Then this is the flow. As I said, this is, for example, just to show you the process I did, the projects I am doing on the APIs. Using the same setups, we tried to use also biotechnological approach for lignin degradation in flow. So we used the technique published years before in order to protect laccase in form of polymer-supported laccase. So the laccase was placed on an aluminum bead and then surrounded with a polymer coating in order to protect it. And these beads containing the laccase can be placed in a glass column reactor, and we can pass through solutions of phenols or polyphenols in order to get their functionalization, activation, or in case of polymers, degradation. This is work in progress. Writing currently the first publication on this to show the proof of concept. This is a picture that shows you these beads contain the laccase on their surface. And in this case, we use the colored solution that get colored only when the laccase is active. So the coloring, you see, this is, you hardly see it, but it's actually, now this green that you might see is actually indicating that the laccase is active in the column. So the principle works. So this is the proof of concept. This is one of the proof of concept pictures. And we have the activation of phenols. So again, this is the flow setup. Let's go to functional polymers. So using more standard chemistries, let's say, once we know the functional aspects, the structural aspects of our lignins, we can functionalize either on the carbons or on the hydroxyl groups. In an easier work, we try to activate the phenolics, and we use different epoxides, which gave us different types of polymers. And playing with knowing the actual loading in phenol groups, right, based on the phosphorus NMR, controlling the chemistries, we were actually able to create lignin-based polymeric or oligomeric materials that displayed various atypical functional groups. So atypical in the sense that the lignin structure themselves does not contain them. So we could produce polymeric oligomeric structures which contain ammonium groups, PEG motifs, which were cross-linked by PEG motifs, etc. So these materials can be used as for surface modification, hard surfaces, for example. They can be used also in other copolymer applications. Activating the carbon is a little bit more tricky. Now, using the OH groups is easy. Activating the carbons is more difficult, but we managed to use a non-lignocellulosic enzyme, for example, lipoxygenase, that has normally nothing to do with lignin, to not degrade necessarily the lignin structure as a major feature, but to activate the carbons, in the sense that we create radical structures on the carbons, so that these carbons then react and can be functionalized. So this can be done either using a lignin directly with the enzyme, or you can use an activator system where our activator, activator in the sense that we have a smaller molecule that shuffles basically the activity between the enzyme and the lignin polymer, where this activator is linoleic acid itself. So the direct substrate to the enzyme can be activated. In an activated stage, before reacting, it sees a lignin molecule, activates the lignin molecule, and we have an activated lignin activated by a non-lignocellulosic enzyme. So that might be a trick to avoid some of the side reactions that you get actually using a lignocellulosic enzyme, right? So this was just a showcase study to actually indicate that knowing the structural features is allowing us to play with, let's say, biotechnological combinations that are not necessarily immediately obvious. We did, I mean, in order to prove, we did obviously some mechanistic studies. I think I have to finish, right? I have 4 or 5 more minutes, if I'm not mistaken. I try to finish quickly then. So again, we functionalize. We use this functionalization in order to produce UV and pH responsive materials. We can do self-healing polymers by using Dietz-Alder reactions, using functional groups attached to the lignin. And then we have a huge part of our research that is based on nanostructures and microstructures. So playing with the right lignin, so using, for example, Kraft lignin, which has these oligomeric, highly condensed units in it. So basically structural features that are predisposed to interact electronically rather than chemically by interactions of the aromatic moieties, right? Interactions that are used to be called pi-pi interactions, which nowadays should not be used anymore as this, because it's much more than just pi-pi. So we use lignins that have these structural features predisposed to do these interactions to create actually nanocapsules. We can place metals in it because we play with the phenols, which are not need to do cross-linking. So we just use the phenols to complex metals, and we use the aromatic units to give us still capsule features. For example, we can use also lignosulfonates in order to entrap then monomeric phenols, for example, thymol, in order to have capsules that release these active monomeric phenols, for example. We can do general studies on the stability of these capsules, for example, because obviously using the right lignin for making capsules, we can tune automatically the stability. So we can decide whether they are stable, at which pH they are more stable or less stable. We can play with cosmotropic or chaotropic effects, etc., etc. The same can be done for tannins, because, as I said, the concepts can then be transferred to tannins, and we can make capsules based on tannins also. This is a project I'm pursuing with Luc Zongo. He is working in a hospital in Burkina Faso, and we try to get that to work as in a theragnostics area. Then we can make particles, obviously, same idea. It's just a solid sphere instead of a capsule. And last but not least, we can use our insights to explain why some lignins can be electrospun and some lignins cannot be electrospun. So recently there was some publication, very recently there was a nice publication from an engineering group in Britain. They were interested in making electrodes on the basis of lignin, and they didn't manage to electrospun the lignin like people before. And then they actually fractionated the lignin and found that a certain mix of fractions could be electrospun. And they couldn't explain why that mix would work. Based on the insights, it is actually, if you look at the fractionation they used and look at the structural features that these fractions display, you could actually make some assumptions on why that was spinnable and other lignins are not spinnable. So they did it. No, they were engineers. They looked at it from the electro point of view. Since a couple of years, we we try to spin all sorts of lignins in order to understand the structural features, and we understood what structural features you want. And we are just finishing our publication, so this will come out very soon, where we make then hopefully predictions on what is spinnable and what is not spinnable, explaining also then the existing literature on that hypothesis that we think we found. With this, I would like to finish. Obviously, all this, as I said, is done in collaborative work, because you need a lot of instruments eventually, and in Italy we have, I mean, now the instruments are there, but maybe I do not have all the instruments, the others do not have all the instruments, so we like to collaborate very, very much. Collaborations are always good in order to get also new ideas, right? To talk to people that see the things from a different point of view. So I like very much to collaborate. These are all the partners I have worked with or that finance, etc. And once more, I would like to thank you very, very much for this opportunity. I very much appreciate that I got this invitation. Thank you very much.
Well, thank you very much, Professor Heiko, for a very important talk today. We learned a lot of insights about sustainable biorefinery. So today, Professor Heiko highlights the differences in main biorefineries and discuss the consequence for the isolated biopolymers in terms of the structural aspect of lignins, also tannins. He has also presented chemical and biotechnological and physical methods for their valorizations on the basis of this structural modification. So he then also outlines about flow chemistry. Actually, I'm very interested in the idea of the functional lignin database, because of course this can provide insights into structural function relationship, which is we know that this is definitely very important issue to study. Anyway, thank you very much again, Professor Heiko. So, okay, now we come to the discussion section. You can actually ask him directly, or you can just write down your question in the Google form that we have provided. But before that, actually, I have a very small question. So, actually, what is the proper and also fast method to elucidate the inter-unit linkage in the lignin, Professor Heiko?
I mean, the only way is 2D NMR. So you have to do it.
Oh, I see.
I mean, even if you, but I mean, even if you do, I mean, it doesn't have to be a quantitative HSQC, right? To get a first impression of the situation, you run in a normal HSQC. It takes 4 hours, and then you get, and then you know roughly what is going on.
I see. Okay. Yeah.
But without the HSQC, it's very, for the inter-unit linkages, it's no other way, unfortunately.
I see. Okay, thank you very much. So here we have quite a lot of questions, but due to time limitation, we only take some of them. So let us share the question that we have received, please. Okay, I hope you, Professor Heiko, can see directly.
You know, I see. So the bottleneck on lignin biorefinery application, large scale, genetic modification. Okay, so there are different aspects to this. Obviously, one bottleneck is always the economic aspect, right? So as you could push to get, for example, organosolv on a really large scale. The question is whether it is worth it, because it has to pay off, right? That is the major problem in all the sustainability approaches, that it has to pay off for the companies, as long as there is no state subsidizing in the back. It can be done. People have to be willing to use actually the products that come out, and there have to be a usage of all the lignin that is then produced. At the moment, there's more lignin produced than is actually industrially converted or valorized. The main valorization of lignin is still just for energy by simply burning the lignin, right? That is still economically the best way to valorize it, which is obviously not maybe the best way that from the pressing needs in terms of environmental aspects that we need. So one bottleneck is clearly the economics behind it. No, if you want people to do it, it has to be sustainable for them economically. Otherwise, it will not work. Then genetic modification is clearly an interesting aspect, but very, very difficult, because you see, I mean, you can modify the plant that it produces different types of lignins, but the point is always to get it out of the plant, you still structurally modify it, right? So that is another, you cannot get rid of that problem. So genetically modifying might work, but you have to do it together with a biorefinery in order to understand how do you modify the plant in order to get out a polymer that you actually intended to get. So it's difficult. And as you know, in Europe, genetically modifying is a very, very difficult topic, right? We have huge problems with genetically modifying anything. So basically, our legislation banned all these genetic modifying approaches. So it's basically something that in Europe is practically not doable, right? So it's from a European perspective, there are also a lot of problems with that. So that is definitely nothing we would in Europe do to arrive at a biorefinery scale, right? That is just impossible from a legislation point of view at the moment. But also that might have to change or might change automatically depending on how the things develop. Then
okay,
I mean, that is you could say much more to that. It's a very good question, but very, very large, obviously, in terms of aspects.
Okay, I hope this answers your question. Next one, if
a variety of protein, what are the critical criteria to select from? Yes, I mean, the selection of raw materials depends a little bit, again, which is abundantly obviously available, right? Which is not competing with, for example, if you have to grow it, which is not competing with land for growing food, etc. That is always a critical point. The quality of the feedstock in the sense of its, how much does it change? For example, if you go for annual plants, how much does it change on an annual basis, right? How reproducible would be the product of the biorefinery actually, right? And the problem with annual plants is if it's a very rainy year, it has definitely different characteristics than in a dry year, and that is reflected by the outputs of the biorefinery, right? So that is one issue, one criteria to select. Again, availability, generally availability on a larger scale would be critical, right? Because obviously you have to feed the biorefinery plant continuously. I mean, the amounts of material have to be there.
Okay, thank you very much. Any response from Andika? Okay, sorry, next question.
Sustainable chemistry concept or whatever we pursue research on. I know the problem. It's actually very, very difficult because you have to find always a compromise between something that works and that is reasonably working and being sustainable. So what we normally do is, I mean, I mean, there's no gold way to actually do it. I mean, for example, now if you do a reaction and you can do it either using a conventional organic solvent and you use 5 milliliters because it dissolves everything very well, the reaction proceeds in high yields and it works perfectly fine. You do a classical worker, but you actually know the minimum amounts of solvents that you need. That can be, at the end of the day, as more sustainable than an approach where you use water, for example, as a solvent, but you need large amounts of water. The reaction doesn't proceed as well as in the organic solvent, etc. So you pollute basically large amounts of water for a worse outcome of the reaction, right? So I would suggest to make a careful consideration of the overall process, not only looking at the reaction, right? Not only substituting, for example, an organic solvent with a less hazardous organic solvent. If you are water, even as a completely benign solvent as such, if then the whole process suffers so much that at the end of the day you need to spend much more resources for workup, for purification, etc., then overall, you know, the green solvent didn't really help in getting the overall process more sustainable. Sustainable is not green, and green is not sustainable, right? So if you really want to go hardcore for green, then you might use much more water than you would actually use in a classical process, right? That is also then also with flow chemistry. Flow chemistry is also nice in the sense that it might justify using an organic solvent, because in the flow setting, due to the higher control, you use actually much lower volumes of these solvents, right? So overall, it might be chemically and environmentally okay to use even an organic solvent, maybe not the most toxic ones, right? If you can substitute one organic solvent with a much less hazardous one without compromising too much the outcome of the reaction, that is obviously a thing that you really should do. But sacrificing the use of organic solvents right from the beginning because you want to be green might cause so many problems that in the end of the day you're actually worse. So it really needs a careful consideration of the whole process, and then trials to see what it causes, right? A substitution of the solvents. But that is the case-to-case decision, honestly.
Yeah, thank you very much. Okay.
I mean, obviously, the greener you are, but you have to consider everything, right? I mean,
yeah, it's very complex.
Liters of water for workup. I mean, that's no point then.
I see. Okay, the next one might be.
That's fine. Okay. So yes, it's a lot of research done on using waste as a resource, not only bio-based but also municipal waste, in order to extract whatever is in there as valuable substances. So this is we're not there on industrial uses yet. So as I see it, it's still a lot of things to do in order to make it really a valuable process, because it's not easy, because the mixture that you obviously have is the fact that you have mixtures, right? That is causing the problems. Because if I cut, for example, if I have only softwood, it works, for example, right? If I have a mixture of biomaterials that go in my biorefinery, that has consequences, in the sense that you mix chemical reactivity, so the process cannot be as efficient as before, and you actually do not really know what comes out as products. So it needs some investigation before you go for large scale, but it is one of the ways to make use of our waste. So doing this urban mining and also using the bio waste is clearly a good thing, a valid research and an important research aspect, but it's still a little bit far from my perspective to industrial use. So it needs a little bit more technological development and understanding what is happening using mixtures rather than single feedstocks.
Thank you very much. I hope this answer is there any question?
Okay, Tannins and Lignin show relative complex. As I said, I mean, the best thing is NMR. So if you have an idea of, if you run HSQC, a normal HSQC, or carbon NMR and the phosphorus NMR, you know the hydroxyl groups, and you know a little bit about the linkages, and then you take it from there. So we'll get a basic idea. NMR is best, to be honest. And NMR, if NMR is not accessible, the problem with IR is always, I mean, there are UV techniques for get an idea of OH groups, phenolic OH groups, so that might be an option. And IR is okay, but unfortunately IR is has less resolution than NMR, so you do not see everything eventually.
Because here in Indonesia, NMR is not so available.
Yeah, I know. The big problem is, and I know that very well. I mean, I know that problem. I know that problem, but IR is really it's not the best. It's not anymore the best thing to get an idea.
Okay, next question.
Yes. Yeah, very good question. I mean, it's the same. It's the same everywhere. It's the same in Europe, etc. As I said, it has to economically pay off for those guys that run the facilities later, right? So as long as there are uncertainties, it's very difficult to actually arrive at a commercialization, etc. So what it takes from a research perspective is eventually to become more practical from our side as a researcher, right? So we need to understand that if you want people to use it, then you actually maybe you have to focus your research on those aspects that will permit someone to produce it on larger scale and other people then to use what he is producing, right? So we need, as a research perspective, maybe we have to become more practical. That is definitely something, consequences of the needs of our times, according to me. So it's nice to go in very deep details from an academic point of view, right? From a researcher point of view. But if it comes to other aspects, we might need to postpone some detailed questions and see that the process gets working and to understand what's going on the large scale, to allow other people to move on in one direction, and then we can go back and focus or derivatize our research in other directions. So from a scientist point of view, I think we have to become more practical. We have to work very closely with those guys that later run the plants. So we have to directly from the beginning talk to people that are interested in putting up a biorefinery, for example, a plant, right? We have to directly work together with engineers, because some things that chemically, for example, are very interesting are practically never doable on scale. So that is something we might, in order not to lose time, we might actually work right from the beginning with chemical engineers, with engineers that construct the plants, etc. So it's, from my perspective, the key is to become more practical from our side.
Okay, I think this is the last question. Actually, we have some question, but maybe due to time
if you like, if you send me questions by email,
okay.
I will answer by email. No problem.
Okay. Thank you very much. Thank you very much, Professor Heiko. Finally, we come to the end of this lecture today. We'd like to say thanks again to the lecturer today, Professor Heiko Lange, for sharing very important information about biorefineries. We also thank all the participants for joining our event today. We do hope that this event will be a rewarding experience for everybody. Okay, Yasmin, I give the screen back to you.
Thank you so much. Thank you for the amazing session. Hopefully, from this session, we can get a lot of new knowledge. Ladies and gentlemen, finally, we came to the last session in this event. As a mistress of the ceremony, I would like to give a huge thanks to Professor Heiko Lange, Dr. Hanggara Sudrajat as the moderator, Dr. Boy Arif Fahri as the head of the Chemical Engineering Department, and also all of our amazing audience. May what we have conducted will be useful for us. Before I close this event, I would like to ask all of the audience to turn on their camera to take photos together for documentation. On the count of 3, 1, 2, 3. Thank you. Even guiding this event, we made mistake or offend someone here. Please accept our apologies. Good afternoon and wassalamualaikum warahmatullahi wabarakatuh.
Thank you very much again, Professor Heiko Lange, for your time. See you in the next opportunity.
Yeah, thank you guys.
Thank you very much. Thank you very much.
Bye-bye. Bye.
Bye.
Bye. Bye-bye.